So,
yes, so please, make contact.
Thank you. I'd like to thank myself for organising this conference. I don't seem as sharp as usual. It's in the fact I've got a corner of my mind thinking about things and organisational things. Can't switch off at the moment, so please bear with me. I wanted to just start by saying thanks to people who have helped me develop my understanding of string theory. So Lou over here, Rulik was my me. I've had the benefit of talking to Jeff a few times recently, which has been sort of very helpful. Tiziana over here, who's my student, but also probably taught me more about string theory than I ever taught her. And Josh, who may have disappeared by now, we've been working on things, and certainly through his questions I've learned a lot as well. It's traditional in philosophy after you thank people to then say that the false things that you go on to deliver are not their fault at all. So take that as read. I put this picture up because there's one other person I really wanted to thank here who some, but maybe surprisingly few of you knew Bob Weingart, my advisor, who for a long time was the only philosopher who had a paper in string theory for at least a decade, I would say. And was a big fan of the subject, and he died in '96, otherwise I would hope he would be here and having a really good time. And Daniel is not here, but you'll also see why I was defending Maudlin earlier. That's me, if you can believe it.
Is that the dissertation?
Yeah.
Who's next to you on your left?
So Barry Lower and Das van Frassen. Okay. Well, a big part of this meeting is to try and form a sort of a shared framework between philosophers and physicists to talk about these things, to talk about quantum gravity and what's happening here. Sorry. To talk about quantum gravity, so I will. Now I'm going to stop working.
You just should use full screen instead of.
Oh, that'll do. Okay. So I will take a few minutes, I think, to explain how you should take my talk, because I think in a mixed group like this there are many audiences and it's not necessarily obvious how you should listen to or what somebody is trying to achieve in their talk. I wrote this as a sort of short essay that's turned into this talk that I wrote in the first place for philosophers of physics, so who I wanted to introduce who don't know much about or anything more than popular level things about string theory. And I kind of wrote this talk to, in the first place, make them not be too afraid of it, to try and show that despite the many kind of complicated technical aspects, there's a lot of familiar stuff in string theory that they will recognize, and to kind of encourage them to work on it. I've got to try and do that in 60 minutes, so I think there's three parts to the talk. Let me go a little past this point. Probably less than 60 minutes. So in that time I wanted to introduce a little bit of the formalism, and then talk about a couple of topics that I think people have discussed a bit and are good examples for philosophers about what they should think about. But obviously I'm covering a lot of ground in a very little time here. But more than that, I'm a philosopher looking at the physics, so I'm kind of a tourist in this subject. And so really, the analogy I have for thinking about this paper and this talk is, it's like an article that you would read in a travel magazine from someone who's just visited a country and hasn't gone native there. So, people have shown me around a bit, and I've seen what seem to be some interesting salient things, and they've explained a few things to me, and now I'm trying to explain it back to my compatriots. So that's a kind of way to be kind of thinking about it. But my selection of what's interesting, it's going to be colored by where I'm coming from, and the way I explain it's going to be colored by where I'm coming from. And so things may well sound a bit different from the way physicists would do that. Okay, that's how you could imagine this addressing to philosophers of physics. I think if I said this something like very briefly along this line to Chris earlier. If you're a physicist, then what should you be getting out of this? And maybe in particular, if you're a string theorist, what might you're interested in string theory, what might you get out of this? Well, as I said, I think a big purpose of this meeting this weekend is to try and form a common sort of language and way of discussing things between physicists and philosophers. I'm taking it as read that you bought the arguments that Chris and I gave you at the beginning, that there is philosophy to be done here, and so it's worthwhile trying to form that common connection and language. So what you can learn is, I think, what I said to Chris, you can learn something about, in the first place, about how philosophers are likely to think about your subject and to what they're likely to find interesting. So it's sort of a step in trying to form that common language. But do remember, I'm talking about, as I said, this is the report of a tourist, so if you're an inhabitant of this country, it's likely that my report's going to sound kind of odd. The things I find interesting might be different from the things you find interesting, and the way I talk about them may seem different from the way you think about them. And no doubt, in some respects, are actually, misleading, and I've got the, got the wrong idea about something.
Wrong end of the string.
The wrong end of the string. Okay, but on the other hand, you can also learn. You can learn about your own. There are many things about your, I will give up on this metaphor in a minute, but there are many things you can learn about your own country by seeing how outsiders see it. So I hope that's also something of value. So to the philosophers of physics, like articles about travel to foreign countries, I hope this will entice people to visit string theory and actually learn about it. And I guess the final thing to both groups that I'd say is, what philosophers of physics need to do is not think about, of course, string theory just at the level that I'm going to be able to describe it here. This is supposed to be an invitation, an encouragement to actually study the subject, go native, so that you can actually think about things more rigorously. But for now, an overview of some of the general technical ideas, so that when you go and pick up a textbook, you'll at least have some kind of idea of what the route is going to be. Okay. So I'm going to start with a very simple system. We're going to start just thinking classically. So I'm going to take a classical string, and let's just think about that. And in fact, this is a really lovely system, if you like, sort of mechanical systems, just in its own right. It's very fascinating. So we're going to imagine a string, and we'll start with we'll put coordinates on the string. Shouldn't say, get that 0. Sigma and tau represent coordinates on the string. It's a two-dimensional object in space-time, space and time coordinate. And we're going to imagine that it lives in a d-dimensional space-time with coordinates x0 through xd.
Is this a relativistic or a classical?
Yes, it's going to be relativistic. Yeah. That's important. And I'm going to assume there's no external forces on it, including no gravitational fields. So we have a Minkowski space-time. And what I say here is I'm assuming the string is closed, though I realized too late I drew you a picture of an open string. But really this string is supposed to be a loop, so this should look like a cylinder, not like a sheet. Okay, from the point of view of the string then, it's natural to think of this in terms of a string in a space-time, a target space-time we'll call it. But from the point of view of, we can invert the picture and think about things from the point of view of the string world sheet, as if that were a space-time. From the point of view of the string world sheet, what we have is a d-dimensional vector field living on the string, and what from one perspective is the motion of the string through space-time is vibrations, oscillations in a d-dimensional field on the string world sheet. And I want to sort of have that picture firmly in mind, because that's how I kind of want to be thinking about things a lot of the time. Okay, so how is this going to behave? It's a string. The first thing that kind of comes to mind is we should have something like Hooke's law, but that's not going to be very good because it's relativistic, and it doesn't seem like Hooke's law doesn't sit very well with relativity. It seems like the tension would go down just because of a Lorentz boost, but that's just a frame change, so that can't be right. There is some literature on relativistic Hooke's law systems, but let's just leave that to one side. But what does Hooke's law say in another way? It sort of says minimize the length, minimize the area over time. Well, minimize the length isn't a relativistic statement either, but something that's kind of, something that's close to that is minimize the space-time area. And so that is in fact going to be the law of the relativistic string. Okay, we want an action which minimizes the space-time area. And, well, there's the action, and then the least action principle will tell us to minimize the area. That's what it looks like in the coordinates that we've got so far. But we can do something slightly neater by writing it in terms of an integral over the string world sheet rather than an integral over the world sheet in target space. And we come then with the famous Nambu-Goto action, which is, if you look at between 2 and 3, really just the same thing with a change of coordinates. I should probably reiterate what Chris said as well. I'm not proposing any new physics here, obviously. This is all stuff you can find from a textbook, but presented in a way that I hope is useful to philosophers of physics. Okay. This action sort of exemplifies the non-Hooke kind of behavior. This quantity T, which I should have mentioned up here, is the string tension. And the fact is, it's constant. It doesn't depend on how the string is stretched in any way. So I think that's an unsort of Hooke's law kind of behavior, where just knowing the length of a spring doesn't tell you how much tension is in it, how much energy is in it. You need to know how the different parts of it are stretched relative to one another. That's going to make a difference to things. Here, all that matters in some particular frame is how long the string is. Okay.
Does the interior of the world too need to be connected?
Sorry?
Do you need to keep connected the interior of the world too, or can there be crossings to this?
So, you mean sort of interactions here?
Well, I mean the surface crossing and separating the interior in several pieces.
So if I understand, maybe we can come back to the end, but if I understand your question, then no, I don't think that's here. I'm just considering, I've just got a bit of string and it's relativistic and it's kind of swapping them out. Yeah. Can it cross? I don't know. So, but I really do want to, I don't think that's going to be important for what I'm going to go on to say. So, one of the things that the conformal symmetry is pointing to is it doesn't care how far apart anything's parts of the string are, just how long the whole string is, thinking in some particular inertial frame. It also has diffeomorphism symmetry with respect to the sigma coordinates. And so there really is no sense in which you can track parts of the string through space. The world sheet really is a two-dimensional space-time object, not something sort of persisting through time. That last comment's for philosophers, I think. You know what I mean. Okay. Yeah. So that square root's not very nice if we want to do quantum mechanics. So there's a nifty trick which you can find in any textbook on the subject to rewrite the Nambu-Goto action in an equivalent form. And the trick involves introducing this h, an internal metric on the string, distinct and not defined by the G metric. It's not, in particular, it's not the restriction of the G metric to the string. It's as if the world sheet itself had a metric. Because it's a trick, it seems that h should not have any physical significance. It appears in the action, but it shouldn't really be making any difference to anything. And that's what we're indeed going to see.
Is it positive?
So it's a regular metric. Yeah.
I mean, signature plus plus.
Oh, no, it's a space-time metric.
Okay.
Sorry.
Plus.
Yeah. In fact, in a minute we're going to set it to -1, 1. Sorry, yeah. So, think about I want to come back just one more time to the unhook-like behavior of the relativistic string. These derivatives, effectively what they're saying is, how much it looks like what it's saying with these derivatives, right? Is how far, in target space do I go when I go at infinitesimal distance along the string? In other words, how far is the string stretched? In different stretching should give different derivatives. But that's a sort of hook law kind of behavior. The fact is, as I said, that h doesn't have any physical significance, so we really could just rescale all these. There is no physical significance to how far pieces are stretched. So to ensure that these don't kind of track how stretching's in the string, we're basically going to have the symmetry of the metric. We can rescale it, and the hook law behavior, sort of unhook law behavior, shows up as via conformal symmetry. We can simply rescale the metric however we like across the world sheet. And this conformal symmetry of the string, in many ways, is one of the most important kind of properties of string theory, and something we will sort of track through as we look at as we carry on the discussion.
So a quick question, Nick, because you said you really wanted to draw a closed string. The topology of the surface is R cross S1.
Yeah, nothing I've said so far depends on that, but I know later on we're just going to be thinking about strings.
Okay, because the worry is that if it's just a line, then there's some issues about whether or not you want to include the boundary as part of the
So usually, the boundary is included at the endpoints are there. Okay. In fact, there are boundary conditions at the endpoints, so
I see.
I love that. Okay, so conformal symmetry is pretty interesting, and despite the fact that philosophers have written a lot about symmetry, I asked a lot of people, I don't know if I asked Jeremy, but I asked a lot of other people whether they'd ever thought about conformal symmetry or read anyone who thought about conformal symmetry in the philosophical literature. The answer seems to be no. So it seems to me what I have in this talk is a list of questions that I think might be interesting for philosophers to think about. This is my first one. Well, what about conformal symmetry? Here's a couple of examples. What is the general significance of conformal symmetry, and how does string theory compare to those? I even asked Malmont, and he didn't have anything to say.
Nick, question. Do you mean just conformal at the classical level, or do you also mean at the quantum level?
I'm at the classical level to start with, but sure, why not the quantum level?
Because n equals 4 is pretty special in that it's conformal at the quantum level and not
okay, fair enough.
It's conformal anomaly.
Fair enough. Okay. We can use the conformal, I had a couple of notes about the conformal symmetry, which was supposed to come before my question, I guess. So first, let me just emphasize, it's conformal symmetry with respect to H, the metric on the string, and not conformal symmetry with respect to the target space. Of course, we have Minkowski spacetime, so the relevant symmetry for the target space is the Poincare transformations, okay, not conformal symmetry. And we do have diffeomorphism symmetry with respect to both the x's and the sigmas in here as well. We can use those symmetries to choose that H is just a flat metric, minus 1, 1, in which case the sigma action simplifies dramatically into this form. The dot is a derivative with respect to tau, the dash is a derivative with respect to sigma, and the squareds, these are squareds on the x's, so they're with respect to the targets. That's the inner product with respect to the target space metric. Okay. So where am I now?
What prevents the world tube from becoming space-like? I mean, you said that the induced metric, or this metric that will correspond to the induced metric, has signature plus minus. What prevents the tube from going?
It's not an induced metric, right? It's just an arbitrary.
The
H, right?
Well, let me ask you. In the previous formulation, when your world tube was just these 4 fields defined on these 2 coordinates,
yeah,
what prevents the world tube to become?
So I start with a string like this. I work in some inertial frame. Why doesn't it sort of become entirely space-like or something? Well, it's the relativistic equation of motion, I think. I don't know. That would require, yeah, I don't know. I think because it's relativistic, I don't have anything more to say about it than that.
You could prove that it does, presumably, because it's a rewriting of the standard O2 thing. So you could prove...
Perhaps the classical solution doesn't. You can prove it for something having high dynamics. Perhaps the classical. If it follows the classical equations of motion, perhaps you can prove it later. But if you're going to sum over these things.
So we're still working, okay, I'm going to shelve that one as well. We're still working classically at this point. Yeah. I don't know. Okay, so this slide I'm just going to write down a series of equations that will sort of come up again later. If this is the action, and you can now compute in the normal way what the canonical momentum is, for instance, and then you can calculate what the Hamiltonian must be, and you can also solve the Euler-Lagrange equations and find that this just corresponds to sort of the simplest relativistic wave equation you can imagine, C is equal to 1, of course. And the general solution to this kind of wave equation is something like this. Following sort of standard procedure, I've replaced the tension with the characteristic string length, and the string length squared is just the reciprocal of the tension. And so we just get an ordinary kind of wave equation, which sort of starts with a point that's sort of the initial position of the center of mass, where the string would be if there was no motion at all. It has a term for the linear velocity, and then it has a bunch of oscillating terms that are left and right moving around. Now it is a closed string at this point. Okay, left and right moving around the string. And so the alphas here are just the amplitudes of the different modes moving left and right around the string. Since we have a mode for every whole number except 0, but we have this term out the front, it actually turns out to be convenient to treat the sort of linear velocity term as the 0th mode, in which case you can now, so if you work on string theory textbooks, you're now at the kind of point where you take this expansion for the x fields, so the values of x, and you plug them into everything and see what you get in terms of the alphas. And so it's one of the exercises that you do is you find that the Hamiltonian ends up as a sum over the modes like this. And if it was an open string, you wouldn't have left and right movers, you'd just have sort of one of these instead. Okay. I'll bring these equations back as we need them, but the whole point here is, again, for the philosophers of physics, this is all just sort of standard, what you would expect to do with a system like this. Okay. So I should have said at the beginning, by the way, the handouts are all on the website if you want to follow along at home. Okay, because of the conformal symmetry, we can now think about taking the variation of the action with respect to the metric, and you get this expression if you solve it explicitly. Because we have conformal symmetry, there is no variation of the action with respect to the internal metric, the H metric. The action is supposed to it's invariant. These alpha betas range over sigma and tau, so we basically have 4 equations here. Again, it's a standard textbook thing to solve these, and what you find is a series of constraints on relating the alphas that look like this, and all of them have to be 0, and we'll define the expressions of this form to be L sub m, which are the Virasoro constraints. So, in a certain sense, we could talk about these a lot, but I want to move on to some other topics, but I want to flag these as being significant. From a physical point of view, this is the stress energy of the string wheel sheet. It's the action with respect to the metric on the string, and the conformal symmetry means that stress energy tensor of the string has to vanish, and so what the Virasoro constraints are saying is basically these things turn out to be the modes of the action. There's a sort of expansion of the action in terms of the L's, and so physically it's saying all the modes in the action vanish. Geometrically, these Virasoro constraints correspond to generators of conformal symmetry. They have, so there's a really nice geometrical interpretation of these. Okay. Let's see. There they are. I just want to say use the Virasoro constraints in just one really neat way to show something important about string theory. So, let's see. Imagine, we're still working classically, but imagine the string's really small and we're looking at it from a much larger scale. So basically it's going to look like a particle at this point. Okay, well, if it looks like a particle and we're doing relativistic physics, then we must have the standard relativistic relationship between momentum and mass. On the previous slide, we defined, a couple of slides back maybe, we defined the alpha zeros, the zeroth modes, to be basically proportional to the momentum. There was an alpha bar for the as well. Putting these two together, square the left-hand side, we see that the mass squared has to be equal to, is given by the sum of the zeroth modes squared, basically.
Sorry, minus signs?
Yeah, so I've got a minus plus 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 signature, so this M is the rest mass. Is that okay? So, but this is the full momentum squared. We can use the zeroth Virasoro constraint, just rearrange it to express the alpha zero squareds in terms of the other alphas. Putting 14 together with 15, we get an expression for the mass which shows them to be the mass basically to be a sum over the modes of excitation modes, the modes of the string. These are all the vibrational terms that were in the solution to the wave equation. We're summing over those. So in other words, the mass of the string is coming from the vibrations. The mass of the string as a particle comes from the vibrations in the string, which is probably something you've heard before. What's kind of notable is I wrote down the Hamiltonian earlier on the previous slide, and it was just this thing. So one thing to know about the string that is sort of weird is you might think relativity, the Hamiltonian should go like the mass, should be like the energy. Energy goes like mass, but no, the Hamiltonian of the string goes like the mass squared of the string. So you're going to pick up, anyway, you're going to see the sort of mass squared in cases where you expect mass. Okay. Quantization. Well, I'm not going to do any quantization. It's clear what you should do. Impose equal time canonical commutation relations on the world sheet with respect to sigma and so equal tau. We want canonical commutation relations. Eta here is a Minkowski metric, and again we've got x and that's the canonical momentum. They can be expressed in terms of the alphas, in terms of the modes. You can imagine the calculation, you just plug in for x and plug in for the canonical momentum when you've worked it out, and you find a commutation relation on the alphas, and up to the fact that this is the Minkowski metric, so one of these has the wrong sign, you're going to get raising and lowering operators, as you would expect in a quantum field. Okay. Very quickly, once you've got, right, and again I'm saying this is what you can expect when you read the textbook. You've got, we had an expression for the Virasoro generators in terms of the modes of the string. We've now got a commutation relation for the modes of the string. Plug the former into the latter, or the latter into the former. You will find these are the commutation relations of the Virasoro generators. I bring this to your attention because I mentioned before that Virasoro generators are the generators of conformal transformations on the string world sheet, and they have, that's classically, quantum mechanically, the operators have this first term, which is the algebra that you want for the conformal transformations, but you pick up this extra central term, which shows that the conformal symmetry has been broken, and to cut a much longer story short, getting rid of this is what's going to set you to the 26 dimensions in this case. Okay. So, the 26, the business of the Kaluza-Klein compactified dimensions brings me to the second question. Are they really spatial in the same sense as the large ones? Is there some way of thinking, well, I forgot the question there. Can they really be thought of, should they really be thought of as spatial, or are they really some kind of representing the states of some internal representation? Are there literally, if bosonic string theory were true, would there literally be 26 spatial dimensions? Or is there an important sense in which, you can answer my question?
No, I'm making it. I was wondering why the energy goes like mass squared on the last slide. Is there any intuitive reason for that?
Not that I can give you quick. I could sort of give you other routes to that idea, but I don't know. No, it's the way we set things up. Okay.
It's something that you can get in the infinite momentum string?
Yeah, that was the other thing I was thinking of saying, but I don't think I have time to say. But I don't know if it's kind of clearer that way either. Yeah. What Tiziano is pointing out is, I emphasized at the beginning how the string doesn't have a Hooke's law behavior, but it sort of turns out if you go to light cone coordinates, where you basically pick one of the, you boost one of your spatial coordinates to the speed of light, things sort of turn classical in that it's not, you're at the speed of light, so you don't actually have an inertial frame. The thing actually does behave classically, and if you transform it back to ordinary inertial coordinates, you get the same thing. But that doesn't really answer your question. I'm sort of pointing that out in case, partly because you will see presentations of string theory that do depend on Hooke's law, but there's this trick of moving to an infinite sort of momentum frame that allows you to do that. Okay, duality. I think these parts of the talk are quicker. Let's hope so. Last time. So I managed to draw a closed string this time. Now imagine, yes, I drew a closed string. The cylinder, though, represents space or space-time. It represents that one of our spatial dimensions is compact, is closed. Okay, and it has radius r, and I've drawn a closed string that's wrapped around it. Okay? And so I've sort of, well, I guess this is two spatial dimensions in the picture I've drawn. There's a spatial dimension up and a spatial dimension around, and I've picked a particular time to draw the string wrapped around the cylinder. And let's call W, the number of times the string is wrapped around is W, the winding number. And what's going to be important as we go on is, classically W looks like it's just a fixed number. We want to have the possibility that if we have an interacting string in quantum theory, and that W can change. The string can change how many times it's wrapped around the string, or wrapped around the dimension, and if I had time and thought about it, you can sort of see how an interaction between two strings can change how many times each of them is wrapped around the string, is wrapped around the cylinder. W is not a constant, it's a dynamical quantity. Okay. We have the same solution for the motion of the string, thinking classically. Okay, this is just the same thing I wrote up before, except instead of that big sum in terms of the alphas, I just write in vibrational terms. And for the purposes of this discussion, we're just going to ignore the vibrational terms, but everything I say will kind of go through with respect to them. So, same thing, I have sort of an initial position where the string would be if there was no motion, then a linear term, and then the vibrational terms that we will be ignoring. But suppose the string is wrapped around the cylinder. Okay, so there's no, but still stationary, so P's 0 and the vibrational terms are all 0. This is then clearly the wrong solution. It's not at a point, it's wrapped around the string. Supposing it's wrapped around W times, and we'll let sigma go from 0 to 2 pi as it goes around the string, then clearly the right solution for the motion of the string when it's not moving at all is this. That tells you how it's wrapped around this dimension. Okay, so clearly what we need to do in this case...
W is an integer?
Yes, yeah. That's the whole number of times it's wrapped around. So our solution should now replace the sort of point with this expression to show, to get the right solution when it's not moving. And okay, let's see. We have the same. I gave you this Hamiltonian before. Once we, that's the Hamiltonian we had before. We can plug in our solution, and now the vibrational terms have completely dropped out. We see. Just working classically, the Hamiltonian has this form. I've just rewritten the Hamiltonian again. So that was a classical treatment. Now we want to quantize the string. And I want to treat momentum as a dynamical quantity. And this is the important part. Winding gets treated as a dynamical quantity as well. So it's not a C number, it's got to be a Q number, there's got to be quantum states for the winding. And we've got to see what's going to happen. Okay. Well, momentum eigenstates are just plane waves, getting that normalization. But we have a string going around it. We're interested in the momentum around the closed dimension, so there's going to be periodic boundary conditions, all familiar stuff. The momentum's going to be quantized. I'm setting everything equal to all the constants equal to 1, and then it's going to be n over the radius, and then n's the rate where n is the wave number, the number of waves around the radius. We want to do the same with W. Well, in here we've got P, and it's a whole number divided by the radius. Here we want something that's a whole number times the radius. So it's clear what we should do for winding. What we need to do is the wave function for winding. That's going to have to be a plane. Here's what we can do. We can make that a plane wave 2. set that around a closed dimension, a closed circle as well, so that we get periodic boundary conditions, so that we get discrete values of, integer values of W. But clearly, setting it around us, looking back at momentum, when we had the wave function around a circle of radius r, we ended up with the reciprocal of r in the momentum. So if we want to get eigenvalues Wr, as we do in this expression, the correct thing to do is have our waves living on a circle with the reciprocal radius, 1 over r. Okay, and you know, this is just elementary stuff you can then check. Okay, what is this other circle? Well, let's call it winding space. It's the home of this wave function, but it's not a spatial dimension. It's not somewhere where we could find another particle. It's another degree of freedom for another degree of freedom for the string. And Witten, in an article back in '96, called it another direction peculiar to string theory. Substituting simply for the momentum back into the Hamiltonian, he's quantized, so at least for the momentum and winding eigenstates of the string, the Hamiltonian is going to have the form of 26, which I've just copied over again for you. Okay. Well, it's pretty obvious that this Hamiltonian has a significant symmetry. Interchange R and W and set R to its reciprocal. Well, there's this constant in there as well. I'm going to not think about that too much. Just run through the very simple couple of lines of algebra, and this change leaves the Hamiltonian unchanged. So, we take the reciprocal of the radius and exchange the wave and winding numbers. Okay, what we saw before, the mass spectrum comes from the Hamiltonian. So, despite the fact that one case we have a string living in a radius like this, and the other one we have the string living in a radius like this, we find the same mass spectrum. More than that, and I'll talk about this a little bit more in a minute, what we've effectively done is, this is momentum and this is winding. We've swapped the roles of winding and momentum. But they are both wave functions living in a circular space. The only thing that's different between the two of them is the radius of that space. So, there's a complete isomorphism between the two theories here, such that, in the first place, one thing, so everything you said about momentum, in one case you can now say about winding in the other case. So one of the things that's going to change is that the dynamics of the spatial wave function are now going to become the dynamics of the winding function in the dual. So this correspondence between momentum and winding is going to be preserved over time. And if you think about it, since the observables I had, so I'm now thinking about one theory. Here's my physical space over here, here's my winding space over here. All the observables over here are going to be reproduced over here. It's the same system up to this change in the radius, and every observable over here, can be picked out by its relation to whatever position and momentum operators in this space. There'll be one over here that has the same relation to the position and momentum operators in this space. The upshot's going to be, not only do I get the spectrum of the Hamiltonian preserved, pick any state over here, pick any state of the system and any operator over here and its expectation value for that state. In the dual, I can do just the same. I can again find another observable, take the dual system, I can find another observable in that for which it has exactly the same expectation, and it's going to be related to the position and momentum operators in just the same way as before. In short, the pattern of observable quantities is going to be preserved by the duality. So, here's a sort of summary of what's just been said. T-duality is a sort of translation between two theories. One theory is on the left, one theory is on the right. T-duality says, take the reciprocal of the radius. I'm going to forget about the L squared. Okay. What it's also saying is interchange. So how is it going to work? Okay. So here's my 1 joule space. The space goes to its a space of reciprocal radius. But we've also interchanged the roles of momentum and winding. So over here I have a winding space of reciprocal radius and some wave function on it. What I also have to do when I change the radii is also switch the wave functions. The winding space wave function over here becomes the spatial wave function over here. Yeah.
Yeah, I have a question about the terminology. So is it better to talk about, there are two options. You can talk about two theories here, completely different theories, and there is an isomorphism.
I guess I'm going to come to... Let me call them joules. I will try and call them joules, okay? And
I see. Or one theory, such that you have a change of variables.
Okay, so you can see why this is going to work out. I've got it every time I have in my theory I have a space, and then I have a winding space of reciprocal radius, and when I go to the joule, I again take reciprocal radii, but I also swap the wave functions, so everything's going to turn out sort of hunky-dory. There's going to be a nice match from one to the other. So I think this is going to get to what you were driving at, Johan. Question 3, how should we understand T-duality? Do joules describe physically distinct situations? Is the left-hand side different from the right-hand side? And I guess that's what Jeremy was asking. In this particular case, what Jeremy was asking Jeff at the end of his talk. Well, normally we'd think of sort of a C number like the radius of space, as making a difference to how things are. But then we also normally think of C numbers as things we can measure and actually determine their values. You can measure the charge on the electron or something by looking at the observables. The duality apparently precludes that from happening. These are C numbers whose values we can't determine, or we can only determine it up to its reciprocal. So we should at least keep on the table the possibility that there really is no difference between these two situations.
Wouldn't you need to show that this survives all the interactions that you are later on going to consider before saying something like that?
Yes, I guess that's right. I believe they do. So, but okay, yeah. I don't see why they shouldn't. I mean, I'm just going to add a Hamilton. I'm running out of time, so... What, I start about 5 past? So about 10 minutes, right?
Yes, 11.
All right. Anyone want to take a break? Suppose they do, so let's just suppose they do, let's just take, the duality is complete. Well, why not? Maybe they should say the same thing about the world, the way they describe it as the world. Except they say incompatible things, for instance, about the radius of the universe. So how are we supposed to understand that sort of incompatibility? Well, the first possibility is these theories are kind of written in different languages. So the first one, I've kind of done something funny in this switch. The first one, I've got target space is this one, okay? And in the first theory, I should understand target space as referring to, let's call it phenomenal space, the space of experience and general relativity and high energy physics, okay? That target space represents space, but in the dual, we have to take it that there's a sort of a retranslation of things, and winding space represents phenomenal space, and then they do say the same thing, they just say it in different languages, as it were. So imagine sort of two languages that had incompatible statements, but they meant something different. A language where yes means no and no means yes. Okay? There's no real incompatibility there. The second way they might describe the same world despite their apparent contradictions is if each of them says rather less than it seems to be saying. In fact, what all either is really committed to is the sum total of things that the consequences of both of them, things that are joint consequences. So in that case, this doesn't, it says target, on the left-hand side, it says target space has radius 1 over R, but that's not a consequence of the right-hand side, which says, sorry, this one says target space has radius R. Does it say phenomenal space has radius R? Well, it can't do, because, I'm sorry. This one says target space has radius R, and this one says target space has radius 1 over R, apparently. On this second interpretation, a way of understanding what's going on, actually neither says that. They're describing the same world, and so both of them are saying target space is either R or 1 over R. Okay? All either one really says is the things they all agree on. Well, it would be really cool, but I am running out of time. One of the things, fortunately, that they agree on is that phenomenal space has a big radius R. If we're thinking about our big space-time dimensions. I don't know if I have time to give you that argument. But what we can say is, on this second interpretation, phenomenal space clearly has a determinate radius, or at least it's not indeterminate up to R and 1 over R. Okay? Our big dimensions are very, very big and not very, very small. And yet, target space, on this second interpretation, has an indeterminate radius. It could be R, it could be 1 over R. Apply Leibniz law, the philosopher's one, not the mathematician's one. Target space is not phenomenal space. One has a determinate radius, the other does not, and in that case, we have an argument that phenomenal space is emergent. This sort of is answering your question a bit as well, Jeremy. Which of these interpretations is correct? And I have a series of quotations that go with the indeterminate radius interpretation that I was just pushing from a paper by Brandenberger and Waffer, from Witten, and from Green. This is supposed to be my setting up for Eleanor and Nick later today, who I think are going to talk about some other dualities, but you don't have to answer this question. But here's a question in the vicinity. Does this sort of analysis that I've given apply to the other kinds of dualities, and do they push in the same, do considerations work in the same way? Okay. You know, I've been asking people all day long to keep their talks short so that we can have discussion, but I told them it wasn't as easy as they thought, and I guess I was right. I think I do want to say this. It's going to be very, very quick, but that's sort of okay, because really this is just foreshadowing of what Tiziano's going to talk about tomorrow, but it is something Jeff mentioned in his talk. Suppose instead of our original action, we decide space-time's not going to be flat, and instead of our Minkowski metric, I'm just going to put in an arbitrary semi-Riemannian metric. I want to talk about this because I think it's just something I haven't seen philosophers talking about string theory acknowledge at all, and it just seems a really huge, important fact about string theory that we should be thinking about. Okay. So, what I want to, I'm not going to show you, I'm just going to explain how the argument goes, and Tiziano will show you. Can I just write down any old metric here? No. It has to satisfy the Einstein vacuum field equation, which is a pretty remarkable fact. So, at least, I'm going to give you the argument to that conclusion. I'll sketch it out. So how would you compute, so how would you go about doing, so now you suppose you want to solve, you actually want to work in quantum mechanics, quantum string theory, and this is your action. What we do in the first play, or we do, I don't do, but what string theorists would do is think about the first order correction in string theory. So the simplest kind of thing, if you're calculating a correlation function, is how I think about it, is you just have a tube going from your initial state to your final state. The first kind of correction you could put into that would have a hole going through the string. That means it's closed off, so genus 1 topology. And first order correction in string theory, we need to calculate the contribution of a surface of a world sheet like this. Time's kind of going left to right in this picture. How could you go about doing this? Well, the action now gives you what is effectively, as I said, a d-dimensional vector field theory living on this world sheet. Okay, and G mu nu just looks like it's it's an inner product on that vector field. So basically, what I have here is an interaction term for the x field. You have this then. Living on here is what's known as a nonlinear sigma model, and it's a system that's been studied. You can now create a second perturbation theory on this given sheet for this quantum field theory. You get divergences, you have to renormalize them. Renormalization means you have counter terms, generally means you have running couplings, and so now we can calculate the beta functions that describe how the couplings run with scale. And this goes back to work done by Dan Friedan. I think 1980 is also the dissertation where he worked this out. And what he discovered is the beta function describing the running of G, the metric, is just equal to the Ricci tensor plus higher order corrections. But this system is conformally invariant. If you sort of summed all the terms in the perturbation series, there couldn't be any scale dependence. There couldn't be any running of the couplings. Approximation, there can't be any running at this order in the perturbation scheme either. Beta G has got to be 0 because of the perturbation, because of the conformal symmetry. Conformal symmetry implies we have to have Ricci flatness, which is the same as vacuum Einstein field equations. You might say, space, that's kind of bad for string theory, right? Oops, that's not Ricci flat, there's a gravitational field in here. Well, what happens when you add in some matter field? And then there's a later paper by Kalan and some collaborators where they work this out, at least for the case of the heterotic string. And you may ask me, Daniel, about the scope of these results in all kinds of situations, and the answer is I don't know how general they are, but their paper concerns the heterotic string. And so they worked with an action which has the same metric term. They added a Yang-Mills gauge field with fermions that couple to it. What do you find? You get the beta function for, this is basically for the Yang-Mills field. Again, conformal symmetry is going to give you the Yang-Mills equation that you want. The only thing is, to get a term with the Yang-Mills field in the Einstein field equations, you have to go to second order in perturbation theory. Sorry, alpha is just another appearance of the tension here. But once again, the same reasoning, conformal perturbation theory, running coupling constants, beta functions lead you back to the Einstein field equations. Get the Yang-Mills equation, and we get it coupled to the gravitational field. Okay. What is the I know. What's the significance of these results? Let me run an argument very quickly. One way of reading these, it seems to me, is that string theory is background independent in a pretty kind of important way. So first of all, we assume, suppose that the string is really a theory of everything. Okay. Yeah. It's a theory of everything, so it includes gravitons. The extra ingredient here is how we should think about the G field, the Yang-Mills fields in the action. It's in the popular interpretive stance seems to be that these represent the behavior of coherent states of the string. So G represents some classic, the classic represents the action of some coherent state of gravitons, similarly to the Yang-Mills field. So what we're really doing in this kind of action when you're quantizing it is, supposing I've got some coherent state of gravitons, it's giving me a curved metric, and I'm now constructing a quantum field theory of excitations and deviations, fluctuations around that coherent state. And there's some evidence for that. There's reasonable evidence for that. Okay, so that's my second sort of assumption there. When I write down an action, what they're really doing is capturing the effective behavior of coherent states. That's the right action to write down if you want to do what I just described. Figure out how quantum fluctuations around a coherent state behave. Put these two things together, if I write down, okay. And it seems to me you have an argument for background independence in this sense. That big G I wrote in there is not just a free parameter in the theory, something I get to just fix there. It is, in fact, representing what string theory would, the consequences of string theory for coherent states of gravitons. String theory really is predicting that coherent states of gravitons will be related to coherent states of Yang-Mills fields, for instance, according to the Einstein field equations. That's a pretty strong kind of result. Okay. The only thing that's left, of course, is if it's a coherent state, it does, you start, at least the way I sort of set things up with, what you should be thinking of is the real action has a Minkowski metric built in, and I'm just exploring solutions where I've got a nice coherent state for that system. There is still a flat metric background in there. That's flat, who cares? That's nothing. Okay. And I've said this is setting up for Tiziana and flagging her talk from before. Forget about that. All right. There's the rest, but I'm not going to go through it. Obviously, I've gone way over time. So, well, thank you, and thank you.
Maybe we have time for one tiny question.
There's no question.
Right?
Well, yeah.
Don't ask me now.
Is it customary in string theory texts to introduce a plus structure by using the whole world-sheet metric instead of just those conformal parts, or are you just sparing us tensor densities by writing it that way?
Say again?
I was wondering, you wrote an expression in which you could basically cancel the volume element of H out if you were to use tensor densities of a certain weight, because it's a unimodule kind of thing. I was wondering, is this the way the string theory books
so what? Yes. So
communicating through our philosophical wariness of tensor densities.
So there may be a question here for Jeff, but I'm glad you asked a bit about what the textbooks show, because what I said here is exactly the way it goes in the standard textbooks. Thank you for those on extra. Yeah.
Good. Okay. Excellent. So thank you, Nick.